let's get started. I just thought I would do impromptu a stream where I try and do a little coding challenge. So I like to make games occasionally, and this one you can follow along if even if you don't have much experience, I guess. I'm going to try and lay out everything I'm doing as simply as I can. First things first is all you'll need for this are 3 programs. You can actually do away with one of them, but I think I'll go in order. The first one you want is a web browser. Everybody has one. I like Firefox. You can use whatever you like. Chrome, I would say Chrome and Firefox are the ones, the best options. After that, you want some kind of raw text editor. You don't want a word processor like Microsoft Office stuff or LibreOffice. Sublime Text is a nice free one, although it will bug you to buy the full paid version every so often. I think Atom, A-T-O-M, is another good one. There's also Microsoft Visual Studio Code, Notepad++, a bunch of other stuff. You can use almost anything. And the last thing that you'll want, or at least that I like to have, is some kind of shell. This will be different depending on what platform you're using. In Windows, PowerShell is a good shell to use, better than the default command prompt. You can type that up in with the start key. You can hit the Windows key and then type in PowerShell, and that'll find it for you. If you're on an Apple computer, you want to use the Terminal app. It's just called Terminal. And then if you're using Linux, you probably know terminals. You can look up the terminal for your particular system. It's probably going to be called Terminal. So what we're going to be doing is I'm going to try and recreate the classic arcade game Asteroids in the web browser as like a web-based game. I'm not going to use any libraries apart from the standard, rendering stuff that you get with JavaScript and modern browsers. First things first is we're going to have to make a few different files. So any web page needs to have an index file. I'm using the command ni for Windows. It's a weird, Windows is contrarian to everything. If you're in Apple or Linux, a Unix-based system, you want to do touch is a way to create a file. Otherwise, you can use your text editor to just make a new file. I like to use the command line because it's just fast. So let's start with the index HTML, actually. We don't need to make anything else just yet. I'm going to try and go as slowly as I can. I tend to speed through these things because I've done them so many times. But if you aren't familiar with HTML, this is like your very basic skeleton for a web page. You can basically just copy what's here. I can't explain it too much. But if you aren't familiar with this kind of markup language, this may be the part where you're going to bounce off. But hopefully you'll be able to follow what I'm doing here. Suffice it to say, all of these words contained in the less than and greater than symbols are tags, and we use those to define our layout. This head tag is something that doesn't appear visually on the page, but we can define certain features of the page and behaviors. Generally, stuff that's in between the head tags gets loaded while the page is loading on your browser. So it can be useful to preload certain things and make sure that the page finishes loading with everything that it needs. Alternately, you can delay loading certain things so that the page appears first, and then you can have like a loading bar that fades away when everything's ready. One thing that we want to have is this viewport tag. I guess we don't need it really, but I like to include it because smartphones like to shrink your web page to fit the screen. And what we want to do here is we want to tell any smartphones to not do that. No, it's initial scale. We want to tell it to not zoom out, and the width of the page is defined by the size of the phone, like the actual thing. We're not going to worry about that too much. Maybe I shouldn't have even put it there because it's distracting from what we're actually trying to do. So, okay. The first tag, probably the only tag we'll need really, is this canvas tag. Because if we're making a game, we need to draw stuff. And the best way to draw stuff in an efficient way is this canvas tag. I've given it an ID so that we can more easily grab the element with our scripting language. So let's go back to the terminal, and I'm going to make two files this time. And script. So we need styles just to save space. I could write everything inline, I guess. I could define all the styles like in this HTML page, but it's nice to have a separate file. So I'm going to do some, let's see, we're going to do this. Browsers like to have margin on the body tag by default for some reason. We don't need that. What we're going to do here instead, oops, what did I tag? Okay. We want our canvas tag. I'm going to do some style sheet tricks to get the canvas tag to be centered in the window. So let's see. Just so that we can see it, I'm going to give it a border. And then, let's see, we're going to say right top. So we do 50% top. Right, left 0. So this is a pretty old. Oh, that's right. We have to decide how big the canvas is going to be. For now, I'll just do this. This is an old, easy way to make sure that a tag is automatically centered within its container. Position fixed. We don't have to worry about scrolling. Fixed position means that as you scroll, the element doesn't move with the rest of the page. We're only rendering the canvas, and we kind of want it to be in the middle of everything, so we're going to have it fixed. I think all of this is good to start, but I forgot one step in the canvas. One other thing we want with the canvas is to define the size of it. And I'm thinking, like, how big should the canvas be? If we're doing asteroids, I think we want to have like a 4x3. But how big should that be? Let's do 1280. I want to say 768. That doesn't seem right. Hang on. I'm going to do a little calculatoring. Oh, 960, that's right. Okay. So we are going to have this size. The last step we need to do here with positioning, we want to have it vertically positioned as well. So top 50% will move it halfway down the page. But we can actually give it a negative margin that's half the canvas height, which in this case would be 480 pixels. Oops. There we go. 480 pixels. And so the top 50 means 50% of the container, which is our the body tag here. That will be the size of the window, the browser window. And then 480 is the size of our canvas. So you can do that simple math to move it down half the container size and then up half of the canvas's actual size, and it'll appear in the middle of the screen. So actually, I can comment this out, or what I mean is, let me demonstrate this. So, right, to actually see this in the browser, there are two ways. You can, at least in this editor, you can actually just open the file in your web browser and it'll look fine. It'll show all this stuff. I prefer to run a Python server like this, and then we can load up on port 8000 the web page that we have created. So I'm going to hide those away, and we're going to go to localhost 8000. It'll take a minute. Assuming I set that up right, yeah. It'll take a minute because this server, this is the first connection we've made to the server. My neighbors are playing music. I hope that doesn't come through. Also, it's possible that yeah, I probably should have waited for the server to spin up. But I don't see why it wouldn't have connected yet. Maybe I should restart it. Oh, no, there it is. Okay. Weird. Never mind. So we've got this. I turned the margin off, so you can see the red border is where our canvas lives, that canvas tag. And right now I commented out the margin rule so that all that it's getting is top 50% and left, right, 0. So it's all the way at the left side of the screen. It's halfway down the body text size. But if we uncomment this, we'll get, the top margin is minus 480. Auto being the second argument means both left and right margins are going to be automatic. They're going to, because we centered it, well, because we've declared the left and right to be 0 and we've done auto, it'll automatically center. And then 0 is the bottom margin. We don't want any margin on the bottom. I think if you change the margin to any number, it won't really have much of an effect here, but you want to have it at 0 anyway. So we can go refresh the page. Bam, we're in the center. Unfortunately, it looks like 960 is too tall to fit. So I think I'm going to change it to 1024. I think 768. Let's see. Let me do the math again. 5 by 4 minus 3. Yeah, 768. So 768, half of that is going to be 384. So we got to change this. You can also use the transform rule and do a translate of minus 50% in the y direction to also vertically center your stuff. But that's a little better. That fits at least in my display, which, some of you may have bigger displays. We could even do some more styling to scale it up, but there's not much to show for our work yet. So, for one thing, I don't like having this bright white background on stuff that I'm working on. So, and certainly for asteroids, it's outer space. We kind of want to have some other colors. So let's set the background color to, let's see. I think that'll be a nice, oh, actually I know. Let's have a really dark, like kind of almost blue, or like a very faintly blue background. 7 and F. This is hexadecimal stuff. I don't think I can take the time to explain that. But in the canvas, we can set that to full 0, which is black. And then back in the browser, there we go. We've got this kind of slate gray almost. I don't know what you would call that. It's actually very, very slightly blue, but very dark. And then we have black for our canvas. And there's a good reason to do that for the canvas, because the way that rendering works, as we will see shortly. Black should be the default background color every time we render a frame. So let's add, oh, I can keep this without space. Let's add a script tag to our project. Actually, can I just do, oops. The nice thing about certain text editors like Sublime is that you can do that. You can tab to auto-complete certain things. It's really handy. Oops, there we go. I'm gonna do that too. No, I don't need to do that. We want this, we want the page to wait until this script is ready to go, so we're just gonna do that. All right, I'm copying from another file this handy dandy ready function. Here it is. This is just a universal function that you can use. It accounts for old browsers, even though we don't really need to, but I like to use it all the time. Basically what we're saying is our function called fun, we're going to wait until the document, which is the web page, has finished loading. All the elements are on the page and it's ready to go. And then we're going to call whatever function we pass to ready. And for us, that's going to be all of our scripting. So having done all this preparation, we're finally at the part where we're going to draw something. First things first, we have to, our script doesn't currently have any connection to our canvas element, but we have this ID. So the first thing we should do is document get element by ID. Oh boy, is it capital D? I always forget. I'm going to double check. I have a reference file. Oh, it is lowercase. So it's lowercase d in ID and canvas. Oh, that's right. But getting the canvas is only half of it. Get context will give us the rendering context of the canvas, and we want 2D. There's also a way to do 3D. That's way beyond my skill set. And we're only doing Asteroids, the original arcade, so we only need 2D. And we're going to call this render context. And the render context object that we get out of this method is how we're going to draw everything for this game. So how we're going to draw? Well, we're going to have a function called draw. And you'll understand why I've made it a function a little later. For now, suffice it to say that it's nice to have a compact, a place where you're keeping all of your drawing. So first thing we want to do is clear rectangle, which is abbreviated here. And we have to pass 4 arguments here. We need the x-coordinate of the rectangle, the y-coordinate, the width and height. And at the start of the draw method, we want to clear the entire canvas of whatever is on there. We want it totally blank so that we can draw the current state of the game, the current frame that we will be rendering. And that means we want to clear the whole thing. So we start at 0, 0. And I could just copy the width and height from our HTML document, 1024 and 768, but I think it's better to reference whatever the canvas size is, and we can do that with our render context. Because the render context, one of its members is the canvas, which has width and height properties, so we can just do that. Luckily, even if we later decide to scale the canvas with style sheet CSS rules, the width and the height is going to be the same as when the canvas was initialized. So these numbers are always going to be, unless we manually change them some other way, these are going to be the canvas's dimensions. The actual tag, we can scale it up or down, but it'll scale, this 1024 by 768 to whatever the tag kind of actual size is. So this width and height are going to always stay the same. regardless of the like actual visual size of the canvas. Anyway, all that muttering out of the way, we've cleared this rectangle. For just a little test to make sure it works, I'm going to do a little for loop. Let's say 2. Oh, that's right. Render context, canvas height. So I'm going to draw some like imitation scan lines. That should do it. So we're going to start at line, we're going to start like 2 pixels down from the top, and then every 4 pixels we're going to draw a line. And the way we do that is render context, move to. So with the render context, we can draw vector graphics, among other things. We're going to do vector graphics because this is asteroids, and that's what asteroids look like. The move to command moves the kind of drawing cursor to a given position. The X position, if we're going to do scan lines, we're just doing, just for a test. This is, we're not going to keep this display. But just to make sure that things are working, we're going to start at x equals 0 with every line. And we're going to start at this variable I. Actually, I'm going to change that. I'm going to select all the i's, and I'm going to change it to y for our y position. So we're going to move to the farthest left point at the current y coordinate. And then we're going to do line 2. So now that we've moved the cursor, we can draw a line from the current position we moved it to any other position. We're going to keep the y the same, and we're going to draw a horizontal line by saying that the new x coordinate is the render context canvas width. So we draw the full width of the canvas from left to right. You could go from right to left, it doesn't really matter. But for the full height, we're going to stop once y reaches the canvas height. And we're going to sort of draw these lines. The crucial part of this is that we aren't actually drawing lines, we're defining vector, we're defining like vector rules. We're defining where lines should be, and the actual rendering will come later. Before this, we do actually have to do this begin path. That's right, that's the phrasing I should use. We're defining where the vector path is going to be. And we're moving this sort of vector rendering cursor to one point and then sort of dragging it across to define a line. So then we do this a whole bunch of times, our for loop completes, and then we're going to say render context stroke, which is how you do lines. And I think we also want to say, just to be sure, we want to define, by default the line width is going to be 1 pixel, and that's fine, we can leave that alone. Or no, you know what? Okay, we should do line width. It's going to be 1 pixel, but since we're drawing like on the pixel line, it's actually going to try to alias that, which means that you're going to have sort of whatever color you decide, it's going to be like faint version of that color both above and below this sort of invisible pixel border. So it'll actually be like 2 pixels wide, but it'll be faint as a way to anti-alias. So we're going to say the line width is 2, and then we're going to say stroke style, which is how you define the color. These names are not great. This is JavaScript we're working with, so naturally some of these are not the ideal way to do things. They're not the most clear, I should say. But here we are. We have our draw function, and just for testing's sake, we're going to clear the canvas with this clear rectangle function. We begin a vector drawing path. For the full height of the canvas, every 4 pixels, we define a line that stretches from the left to the right, horizontally. Then we set our line width to 2. We want to have a white line, and we call the stroke function, which will, in one method call, fill in all of the lines that we've defined since begin path. For safety's sake, we'll call close path so that having drawn all these lines, we've told the browser that we're done drawing vector stuff for now. We're done defining vector paths. I don't know that we totally need this, but suffice it to say, we'll keep it that way for now. Having done that, let's call the draw function, because right now that we've defined the function here, this is our definition, but let's actually call it and see what it does. So I'm going to switch back to the browser and refresh the page, and look at that, we have all these thick white lines. It kind of looks like an optical illusion, actually. It's also very ugly, so I'm going to switch back to the text editor, and the first thing we're going to do is get rid of all these. Instead, we'll use those rendering calls, the vector drawing, to draw the classic asteroid spaceship, this little arrow-headed shape. So I defined, I'm going to copy, I did some work the other day on this, just to refresh my memory. So I'm actually going to go up here, and I'm going to, oops, I don't want that. I'm going to do this. I'm going to bring in the ship shape that I defined earlier. Don't worry too much about this int 8 array. This is a thing I like to do for potentially saving memory and performance reasons. It probably doesn't make that much of a difference in a game as small as what we're about to make. But the one thing I do like to do is that defining all of these points, there are a few ways you could do this. You could have an array, a list of objects, kind of like, you know, you could do like this and have a little object that has like x0, y10. You know, you could do like something like that. That takes up a little more memory. It might be easier to read and work with. I don't think this is too much clunkier, but it is a smaller memory footprint, and I just like working with this. Even if the performance increase is minuscule, it just kind of, I don't know, it tickles something in my brain. I like doing this way. All we have to remember is that the even-numbered indexes are y positions, and the odd-numbered indexes are x positions. So in order to draw our ship, we do the same thing. We have this begin path because we're going to draw a vector. And then I'm going to write another for loop. This time I equals 0. We're going by indexes, so I'm going to use I. I is less than ship lines length. I plus plus. And then the way I've defined this, because I've looked up, you know, old screenshots of this arcade, Asteroids arcade, and there's not a continuous line shape that you can draw. It's more like 3 lines. There are 2 lines that are kind of an arrowhead, and then a third line that is connected in the middle. And that's what these points define. So I'm actually going to draw 3 separate lines. Actually, in order to do that, rather than incrementing only by 1, I'm going to increment by 4. We got to increment by 2 for each line, and we got to increment by 2 for each coordinate. This pair is a coordinate. And then we have to do that twice, because this coordinate is the start of one line, and then this is the end of that line. So each iteration of this for loop should be 2 coordinate sets, which is 4 indexes in my array, or 4 indices, I should say. So, like we did before with the scan lines, we're going to do render context move to move our cursor to the start of the line position, and that's going to be ship lines. There's going to be ship lines I for index, the ship lines I plus 1, because if I is 0, we're starting at the beginning of this array, I plus 1 is going to be the y position of the first coordinate set. Then we have render context, line 2. I'm doing a lot of autocomplete, so I hope this isn't too confusing. I'm going to do ship lines I plus 2, because 0 is the first coordinate set x, 1 is the first coordinate set y, 2 is going to be the second coordinate set x. Then we're going to do ship lines I plus 3. And since we only have 6 coordinate sets for 3 lines, this loop is going to run 3 times, draw 3 lines. Simple. So our render context, now that we've done that, I'm going to call the stroke method, not stoke, stroke method, and I'll put a little space and do the close path method again. And actually, the way that Asteroids looks, as I remember it, everything is just white lines of the same density, of the same width. So we can actually call, we can actually set, I should say, line width and stroke style once. Oops, there we go. We can set these just once and they'll stay that way. Actually, I think we want just 1 pixel width for Asteroids. So there we have it. I've got my ship lines as defined here. These are x, y coordinates, 6 coordinate sets. We're all ready to go. We're already calling the draw function down here to draw just once. And let's switch back. The lines should go away and we'll see our ship. But look at that, it's way up here in the corner and like most of it is not even on the screen. And that's because I defined the coordinate set for the ship lines based around like a center point where some of these values are negative. So if we only draw the ship lines with this coordinate set, we're going to draw it off screen. So what we need to do is we need to define like an object that tells us where our ship is. So I'm going to say our ship is at, let's see, 100. And let's say, I don't know, 120. So this will be our ship's x coordinate and our y coordinate. With the ship, I'm doing it this way because we're going to be giving the ship over the course of programming a bunch of other properties that might not be numbers. So we can't just give it all an array of numbers. We have to adapt, and this just makes things a little easier because we can just call by name certain properties of the ship. So having defined this, we can modify our drawing call. We can say ship.x plus the ship lines x coordinate and ship y plus the y coordinate, and then do the same for this. And if we return to the window, now we actually see the ship rendered. 100 pixels x, 120 pixels y is going to be somewhere around here in the middle. And then we've defined our ship coordinates here, the lines that define our ship, to be something like this. Having done all that, we still need to do something else, because our ship is going to be facing a certain direction, as we can rotate it in Asteroids, and it's not always going to be looking left. We need to know which way it faces. So I'm going to add this theta value, which is going to be in the range of 0 to 2 times pi, because for whatever reason, not for whatever reason, but we work with radians rather than degrees in JavaScript. You'll see what I mean in a minute. So I'm going to say math.pi, oops, hit the Alt key by accident, math.pi divided by 2. math is a global object and pi is a constant that is stored in the system. So we're going to divide pi by 2, which is a quarter rotation, so that instead of pointing left, sorry, instead of pointing to the right, as the ship is doing now, giving this theta of pi, half of pi will rotate it facing downwards instead. So how do we do that? Well, this gets a little complicated. We get into trigonometry. What we need to get is the cosine and sine of the current radians. You know what? I'm gonna no, theta is fine. You need to get the cosine and the sine of the angle the ship is facing. That's really easy because it's just a method that is provided to us by the math object. So we're going to call this on ship theta, and we're going to call math sine on ship theta. I had to look this, excuse me. I had to look this up because I didn't remember exactly how to do rotational transforms. Suffice it to say, the cosine and the sine, we calculate them here because it's going to be the same cosine and sine for each line segment for every coordinate point that we're moving to in our vector graphic drawing. And it's just better to calculate that once and then reuse it. And the way that we use it is ship X and ship Y are going to be untouched. Those points are the center point that don't get rotated. So we don't touch those. Instead, we're going to do, if I remember correctly, I think it's cosine times the X coordinate. And then we're going to also add the Y coordinate. We're going to do sine times the Y coordinate. This gives us the rotation of our X coordinate. The Y coordinate is kind of like an inverse. We do sine of the X coordinate. Oops, let's do a little space in there. Minus cosine times the Y coordinate. Things are starting to look a little messy. So in order to keep things compact, I'm going to do, say, I'm going to move these out and just calculate them on separate lines. I think boy, I need to look at what I'm doing. I like to normally keep all this stuff in line to save space and not bother with extra memory that you end up using by defining variables to hold these values, but for the sake of the tutorial, I'm going to do that and make things easier. So we're going to say rotated X and rotated Y. We're just going to define these variables. I'm using var even though I think the let command is supported by or the let, whatchamacallit, I could use let probably and it would be fine. I'm using var because that's more compatible with older stuff. But we're going to say rotated X equals this, rotated Y, no space, equals that, and then we can do that. We can add those in here. Yeah, you could also define, if you wanted to, you could define methods to calculate each of these and then just call the methods. I don't think it's much better or worse to just do it here like this. Because of course we're going to be making a method shortly that will compact all of this even more. So we do have to rotate all 4 coordinates in our line. And I'm going to reuse the rotated X and Y for the starting position and the ending position just because it's better than defining, in my mind, it's better than defining even more variables. So then, here we go, rotated X, rotated Y. And of course, this code is so short that you're unlikely to pollute one rotation calculation with a different result. So let's just double check our work. The x-coordinate, these should both be the first x-coordinate at the starting point, which it is, index 0. Then we've got index 1 is the y-coordinate. Index plus 2 is the ending position x-coordinate, and plus 3 is the ending position y-coordinate. We do cosine times x, sine times y for the x position. That looks good. We do sine times x minus cosine times y for the y position. That looks good on both of these. Okay, I think we're all set to go. So let's switch back to the browser and reload, and voila, we're pointing down instead of to the right. We can make this theta anything we want. I could say 1, let's say 1.0 because it's a floating point value. We can reload, and now we're pointing at a different angle. This works with any value you give to theta. We'll rotate around it with this formula here. So point of order. This is nice and all to draw the ship lines, but if we want to draw other objects like asteroids, we're going to have to rewrite all of this again. That's not good. So what I'm going to do is make another function. Let's say draw line segments. So what we're going to do here is we're going to pass the render context. Or maybe we don't need that. For now, we're going to keep the render context is going to be available to all of our functions in this closure. Probably if you were making a rendering library or an engine, you probably want to have something like, render context getting passed down into your drawing methods. But for now, we're going to just leave it global. So for our draw line segments function, we need a few things. We're going to have the x and y positions that define the center point of our object. We're going to have line segments array, which contains our coordinate sets. And we're going to have theta, which is the rotation of those coordinate points. And the reason I call this draw line segments is because with each line, we're moving to a starting point and then drawing to an ending point, rather than drawing a continuous line. Because we could, and I will shortly, draw a different shape that has one move to call. We move the cursor to one position, and then each coordinate point we draw a line from the previous coordinate to the next. So it's a continuous call of move to, line 2, line 2, line 2, line 2, line 2, and then close path will actually draw a final line from the last cursor position to the starting position that we defined immediately after begin path. So for now, all we're doing are these separate line segments that have a move to call and then a line to call. So what we want to do is, first of all, I'm getting ahead of myself. We want to copy these lines because we want to define the cosine and sine of our theta, but we don't want ship theta, we want the passed in arbitrary theta for any angle of whatever we're drawing. Next, we want to have our for loop, which this time will take the line segments array length. Then we want to do the contents of our for loop. But we're going to have to do some manipulation here. All of these instances of ship lines become our line segments object array. They become our line segments array. Ship x, we can get rid of that. X and y are provided through arguments in the function. or parameters, I should say. The parameters x and y are provided as arguments to the function. We do need to copy these, which we initialize them as null objects, which, come to think of it, is not great. I'm going to say that we want to tell the interpreter what type of objects these are. One of the weird things about JavaScript, and it's just the nature of the language, the way that browsers work as well, is that this language gets interpreted in real time, sort of, and it has to get compiled to lower level languages. And if we just have this call, on lower level languages, you need to define what type of variable you have. This call will just initialize these two names, these labels, as pointers to null objects. And then later, once we actually define what value they have, once we assign a value, the pointer is going to point to something else. It's going to drop the null object, create a new object that is, in this case, it'll be a floating point number, which is, for simplicity's sake, a floating point number is a way to represent a decimal value. But the way JavaScript works, you can define what value your variable starts with and save a little bit of headache, void a little headache on the part of the processor, on part of the interpreter, by telling it, hey, look, this object is a floating point number by saying 0.0. It'll set aside a floating point number, and I don't know, it's just a little optimization that probably won't make too much difference. If we really wanted to optimize, we would get rid of these things entirely and move both of these, what's the word I'm looking for? We would move each of these in line and replace the variables entirely. For the sake of legibility, I'm going to leave it as it is, and this will be just an example of good coding practices, I think, in JavaScript. So we've got our drawline segments. You'll notice that I haven't put anything else, like the begin path, stroke, close path inside of here, and I'm not going to explain why just yet, but I will later. So for now, we can get rid of that. We can get rid of the for loop. And now we can just draw line segments. We can say ship.x, ship.y, ship lines. There we go. And ship.theta. And now, so that we see a difference, I'm going to change the theta to 1.5. And you know what? I'll change the x and y positions so that we see a difference. Let's do that. So I've moved it further to the left and further down. I've rotated it more clockwise by a little bit. And this drawline segment, if I've done it correctly, the drawline segments function call will look identical with our new position and transforms. So let's reload. And there, the ship looks the same. It's moved down a little bit and rotated a little more. So breaking all this out into a function is great because we can just call this drawLine segments method whenever we want to draw any collection of line segments. Having done that, though, we should have another function. I'm actually not going to leave a line in between. We're going to have another function called draw. Oh, you know what? So if we want to draw multiple things, we could try and be really clever and call our begin path and close path a bunch of times, and then we only have to call stroke once, and it'll draw all these lines at once. I don't know which is actually more efficient. If it's better to call stroke once per smaller vector graphic, or if you want to wait and call it all at once. So instead, I'm actually going to move this stuff into our drawLine segments call. I'm going back on what I said a minute ago. I'm actually going to just, all of this will be contained in drawline segments. We begin our vector path, move to line 2 a bunch of times, call stroke, which draws the lines, and then close path just for safety's sake. Um, really, we're calling close path in here so that we don't um, collide with any future calls to the vector drawing methods. But now that we've drawn line segments, we want to draw a continuous shape. I'm going to say draw closed shape. So that's going to have some of the same things. Instead, we're going to have, let's see, chords, short for coordinates, and then theta for an angle. So this method is going to be much like our draw line segments. In fact, I'm going to copy all the code to save a little time. This is potentially a little dangerous because you can make mistakes here, but we're going to be a little careful. What we want to do here is a little bit of magic. And we're going to start at 2. So I'm just going to type this up first and then explain now. So what the heck have I done? With our draw closed shape, we don't want to draw each line. We don't want to, move to point, draw line. We don't want to do move to line 2, move to line 2 every time. Once we've done the line 2, because move to moves the cursor without creating any shape. Line 2 creates a line from the previous cursor position, but it also moves the cursor to this position. So now that the cursor is at this new position, if we're drawing a continuous sequence of lines, we can say on the next iteration of the loop, we can line to the next coordinate point. So for that reason, instead of drawing 2 sets of coordinates with each loop, we only draw one coordinate set. So our iteration count goes down to 2 instead of 4 indices. But of course, we need to have one move to call that starts the whole thing off. So it's a little redundant. We're repeating ourselves a little bit here, but as far as calculating these, but we call move to once. We start at the second coordinate set in our collection of coordinates for this shape. And having done move to once, we can line to for the rest of the coordinates. And there's one other thing I need to change. In order to close the shape, we want to call close path and then stroke, because close path will then draw a line from the last line position to the starting position here of the cursor. So we've got our draw closed shape method. Now we need a shape to draw. So let's see. I'm going to put this one above the shape. We're going to have asteroid chords. I'm going to make it an int array again. But if you're following along, you can just do a plain old, untyped array if you want. I like to have a typed array. Probably the simplest thing would be to do an octagon shape. I'm going to try and pull up, if I can find it. I think I defined, oh, here we go. I created, this is a project I've done before a bunch of times, and it's the sort of thing I do every so often just to, it's almost like a comfort activity, if you can call it that. So let's see. I'm just cleaning up my old code so I can present it here. But I think that'll do. So here's our coordinate set for the asteroid. Looking at it, it might be a little small compared to the ship. I might have to adjust these later. But we have our source asteroid coordinates, and every asteroid is going to look the same for simplicity's sake. And having drawn our ship, we're going to call the... let's draw them together for now. Let's do the draw closed shape method. I'm going to double check. Yeah, none of these coordinate points overlap. So the close path will actually be useful. When I say overlap, what I mean to say is that there aren't any duplicates. We don't have an object for our asteroid yet. We'll do that in a little bit. But for now, for testing, let's say 600, 400. And we have our asteroid coordinates. There we go. Let's just do math at random. We'll just do random. Because our asteroids will start with a random rotation as well. It won't actually affect the hitbox because the asteroids, we're gonna deal with collision eventually, but for now they're gonna be random rotation and it won't really affect the gameplay. It's just a visual element. So having done that, having done all of that, we've got our ship. The asteroid, let's see, I said 600, 400. The asteroid should appear around here, and it might be only as big as the ship. It'll be kind of small. But it hasn't appeared, and I've got to figure out why. See, this is why it can be a mistake. It's easy to make mistakes when you copy code like that, because line segments is not the name of the parameter that we're using. We want coords, and so now it should work. And there's our little asteroid. It was a little further over than I said, but that's our asteroid. It's kind of simple looking shape, but it's a little rocky. If we reload, it'll be at another random. Every reload, it'll be a random rotation. All fine and dandy, seems to be working. One other thing we can add is scale, which I think I may as well do for the asteroid. Since it's so small, I'd rather not go through and manually change these. So for simplicity's sake, we can add a scale variable. I'm going to say, let's see. I think we'll have to pass in the variable because I don't think that you can do default values for parameters in current JavaScript implementation. Nevertheless, let's see. We'll just apply, the scale is going to be just a one-dimensional number, so we can multiply the scale by both rotated values. We don't want to multiply this scale by our center position because that'll move it further away from the origin point, the upper left corner of the canvas. We don't want to do that. We instead apply the scale to the rotated coordinates. Having done that, we got to add our scalar value here. So let's say 3 times size. Nope. JavaScript didn't like that. Let's see what I've done wrong. This is half of development is screwing up. It says it's line 64. Oh, I typed equals instead of plus. My bad. So let's do that. Refresh. And I've only scaled it vertically, or I haven't scaled it enough in the horizontal direction. That's interesting. Why is that? Maybe I need new glasses. I think I must have typed a plus somewhere by accident instead of a multiplies. There we go. So that's all working. This will actually be useful because if I remember correctly, we'll need to have asteroids of different sizes. So we want to have this scale value so that we can use the same asteroid coordinates for drawing asteroids, but we can make it any size we want. Now, we've got our ship. Our ship object can be just a plain JavaScript object. We only have one of it. But the asteroid, actually, we can even make the ship into a class if we wanted. For now, let's leave it alone, and maybe we'll come back to it. Asteroids, though, we're going to need a whole bunch of them, so we should make a class definition. I'm going to use the old way of doing it because classes don't really come up in my everyday JavaScript programming, which is not all that much. It doesn't come up in web development very much, but so I don't know what the current standard is for class definitions. It's probably the ES 2016 standard or something, which is bogus because they come up with a new standard every year and nobody is, I don't know, Windows is holding us back in web development. Suffice it to say, I remember the old definition, which is going to look something like this. We're going to define a function, but we're going to return this. We don't strictly have to, but we're going to do that. If I remember correctly, yeah. And then we're going to use this. This is a keyword that defines, it defines the current context, sort of. It allows us to assign it allows us to assign members to an object, like this asteroid. So the asteroid is going to have a few things. It's going to have an X position. It's going to have a Y position. It's going to have a theta, which we can actually copy our 2 times math pi from before. Although I usually like to make tau. Whenever I'm dealing with this kind of stuff, I like to have my own 2 times pi variable constant, I should say. I like to have this 2 times pi constant because pi is only half the radians of a full circle. Tau is the full radians. Multiplication can be an expensive CPU call compared with addition, and certainly when compared with just referencing a variable in the limited scope of this closure. Or no, it's not a closure, is it? It's just a function call. Within the limited scope of this function, referencing an existing constant is much faster than calculating 2 times a floating point constant, which in this case is pi. So we're going to cache that effectively as a constant. So with the asteroids, they will appear off screen and slowly move on screen. So what we want to do is we want to actually oh, that's right. We want to scale. Sorry. I'm getting ahead of myself. This does scale. Let's say it's scale 3, because 3 looks about big enough to me. At any rate, we've got our asteroid. And when we first create our asteroid, effectively this function gets called, these variables get set. That's why we can call the math_random function, and we'll get a different angle every time we make an asteroid. We also want to set where the asteroid appears on the screen. And the best way to do that, well, so they appear on the screen edge. And there are a few ways we can do this. I'm going to say, so let's initialize these. Boy, I'm trying to think of the best way to do this. I'll leave those alone for now. I think we're going to have, let's say we're going to have two cases. We're going to say, it's going to be random again. So we're going to say math.random, if it's less than 0.5, let's do some pseudocode. Comments are really great in coding. You can let people know what you're talking about, where you're coming from, and you can also kind of pseudocode. You can write out what you want to do in a readable way that's not really code, but it's something that will let you know what you're going to do if you're going to do a bunch of things at once. Pseudocode can also be just a really great way to plan out any programming. You can entirely pseudocode with comments like this and then start actually writing code once you've worked out how things are going to work. So for positioning our asteroid, let's do some pseudocode. I'm actually going to even comment this out. Oh, goodness. I'm going to just comment this out for a minute. Yeah. And we're just going to pseudocode. So if, random, yeah, let's say randomly from top, bottom, or left, right. If top, bottom, let's say if it's coming from the top or the bottom of the screen, actually, yeah, let's do commas, because it can be, the asteroid starts at a position off screen, and an easy way to do that is we can just say, hey, it's coming from some place just barely off screen, like the size of the asteroid, right? If it's from the top or the bottom, then we say, the Y position is the diameter of the asteroid away from the screen edge, which I'm mistyping a little bit here, which we can specify a little clearer. If top, it's 0 minus diameter. If bottom, it's canvas height plus diameter. And we have something similar for, else if left, right. We can have X position is the diameter of the asteroid away from the screen edge. If top, if left, 0 minus diameter. If right, canvas width plus diameter. Because the coordinate system, for just about any rendering software, any computer rendering, 0 is going to be the 0 for the X coordinate is going to be the left edge of the screen. For a viewer facing the screen, it's going to be on their left, and Y equals 0 is going to be the top. So we start at the top at 0, and we start at the left at 0. Simple. Then for top bottom, X is random between 0 and screen width. And then I always like to put X first and Y second. That's a pretty common way to do things. So I tend to write them that way as well, even if I'm pseudocoding. X is going to be random between 0 and screen height. Or sorry, Y is going to be 0 and screen height for left, right. So let's actually work this out. Math.random gives us a number between 0 and 1 exclusive. So it'll never be 1, but it can be 0.9 repeating forever. or it can be 0. So if we want to have a random chance of 2, we can say, hey, one case is going to be less than 0.5, else the other case. So let's say the first case is top bottom. Let's set this .x equals math random times, that's right, screen width. So that's going to be render context canvas .width. There's a little problem. We want to have the render context available to us. The var keyword will hoist this variable to the top of the context, in this case the function here, but for readability's sake, just so that we know render context is available down here, I want to put it visually up here. I don't know if this is a good coding practice, but this is what I tend to do in JavaScript at least. So before I get ahead of myself, math.random, we're multiplying it by the canvas width. Simple. That's all we're doing is saying, hey, look, give us, in a range of 0 to, almost 1.0. Multiply that by the canvas width, give us our random x position. Y needs to be the asteroid size. So the trouble here is that we haven't defined how big the asteroid is. I'm going to say, looking at my coordinate set, the biggest number is 18, but I'm going to say that's 16. Hang on. Size. I'm going to say that 16 is the actual size of the asteroid. That little point that's 18 pixels away from the center. Oh, you know what? It might actually be bigger. I'm not looking at this right, because these are positions. If you rotated one of these positions, if you calculated the distance from 0, I think most of these positions are bigger than 16. Suffice it to say, we can say that the asteroid looks bigger than it actually is, because we can argue that it's meant to represent sort of a 3D object, and so the actual edges of the asteroid would be like farther away from the camera and the ship won't hit it, something like that. You can make your argument. For simplicity's sake, and because it's a multiple of 8, and we programmers like multiples of 8, I'm going to go with 16. So we can say y is asteroid size, and then we can use math random again. But this time, I'm going to say math random less than 0.5. So what have I done here? Our rule for the y position is that well, we don't even have to say 0 minus the diameter is the same as -1 times the diameter of the asteroid. Oh, but I can't really do that, can I? All right, we have to do something else. So I'm going to call if math, we're going to do math random less than 0.5 again. We're going to say, if it's less than that, we're going to say negative asteroid size. Else, we're going to say render context canvas height plus asteroid size. Simple enough. Now we can do the same here, but we just swap x with y and width with height. So in this case, the y position is going to be a random location along the height of the canvas, and the x position is going to be either just beyond the left edge of the screen or just beyond the right edge. And with that, we've converted this pseudocode which really I should have put it before the code block. But we've converted our pseudocode into actual JavaScript code. There's a problem here that I skimmed over it a little bit, and I'm going to move these up here before doing that. But our asteroid has a scale of 3, so it isn't actually going to be the 16 pixels radius that I defined for it. Also, oh, I said diameter, which is wrong. It's actually going to be the radius, because the x and y coordinates of the asteroid are the center point, and the size is the radius of the asteroid, not its diameter. So 0 minus the radius means the center point will be far enough the asteroid is just off screen. Had to clear that up. That was a big whoopsie. But moving on to my other point, this asteroid size will be wrong, because the scale of the asteroid is not 1, it's 3. So instead, we're going to have to do this dot scale multiplied by the asteroid size in both cases. Not, I should say in all cases, because we have 4, not just 2. And this dot scale. Done. So having done all that, we have an asteroid constructor, which gives us a random rotation. It makes the scale 3, which is going to be the largest size of boulder, at least for now. And it positions that asteroid at a random position just off screen. Okay. I'm going to move on to the next step after a quick break, because my laptop is making a lot of noise and is running low on battery. So I'll be right back. Boy, this laptop has a terrible battery life. Anyway, we made our asteroid object our basic starting point. But having done that, we need to do a little more. Okay, so I made a little... I'm going to reorganize this script a little bit, because we should order things, I think, we should order things in the order that they're available to later functions and methods. And this asteroid, I want to give it, I think I want to give it a render method. So the first method we're going to give this asteroid, that's the thing. That's the nice thing about this, about making a class, is that we're going to give it a function called render. Well, you know what? Yeah, render. I was going to say we're going to call it draw to keep in line with this, but actually I'm going to say we want to call this render as well. Sorry, I'm doing a little renaming in the middle of programming. Not very good practice. Oh, and that's right. I'm still doing the old method of class definition, and it looks a little weird. It's not the best. The updated version is much better, but I can't confidently work in it right now, so I'm just going to go with this. Our render function is pretty simple. We're going to do the same thing we're doing down here. Draw closed shape. I'm going to comment that out because we're doing things the better way now. But I'm going to leave it there for reference. We're going to do draw a closed shape. And this time we're going to say this dot x, this dot y, because we're referencing the Asteroids members, our member properties, I guess. Asteroid chords. That's right, theta. And scale. I should probably give scale. While we're at it, let's add scale to draw line segments as well. Oh no, I need to do them here. I'm just going to do some fancy programming magic to type a bunch of things at once. So like here, we've added scale to this. I will have to define the scale. I'm going to make the ship a little smaller because I think it's too big. I'm going to bump it down to 0.75 size right now. Great. So our asteroid render function method, the render method for asteroid is all set up. I'm going to then create an asteroid. Let's call this test asteroid. I'm going to say asteroid, new asteroid. There's a problem. Okay, we can't do this yet because we've been doing a lot of drawing. Oops. Oh, you know what? We can't. I'm gonna have myself. I'm gonna say new asteroid. And we're gonna, right now it's gonna be positioned randomly off screen. So I'm gonna have to change the X. I'm gonna move it to, let's say 800. Um, 500. Now we can say test asteroid render. And if I've done everything right, there it is. That's our new asteroid. We shrunk the ship down. That's our new asteroid that we created with as an object. So the problem is, so far we've just been drawing things once. We're only calling the render function once. We're drawing it and letting it sit. But this is a game and things need to move. So what we want to do is we want to wrap this render function in a loop of some kind. In JavaScript, in the browser, the way that we do this is we create, I'm going to call this frame step. We create a function that we then call with this very special method, request animation frame. So this function down here, this waits for the next time that the window is going to render an image, and then it calls whatever function we gave it. It's kind of a set timeout, but very specified. And within that frame step, in order to make a loop, we want to call this again. And this will go until you close the browser or refresh or what have you. And that's all well and dandy. I think, yeah, okay. Here's what we're going to do. We're going to get rid of that. We've got our test asteroid, and our render call is going to draw the asteroid, but it's going to be off screen. And having called this, we've got our frame step. This function is going to get called every time the screen renders. and that's going to be based on your monitor's refresh rate. Typically that can be like 60 hertz, which is 60 times per second. It's very fast. And that's why in video game development, you have to be very mindful of resources and how much processing you're doing every frame. Usually you can do things less frequently than every frame, or you can just minimize all of the stuff that you're doing every frame. So this will call render every frame, but we're not actually doing anything to our ship or the asteroid, so it won't look any different. We won't see a change. To see a change, I'm going to do stuff to the asteroid. So asteroid, let's see, we're going to say, that's right. We're going to give the asteroid a velocity. This dot xvel and yvel. We're going to start at 0, and we're going to define that velocity. We're going to define that velocity by... Oh, that's right. I've made a little mistake. I'm going to get rid of this pseudocode as well, because it's a little bit much. I made a slight mistake, which is that in asteroids, the screen edges loop around. They wrap around so that when you pass the edge of the screen, you return to the other side. So that means, in the original asteroids, that means that the center point of the asteroid passes the screen edge. It should appear on the other end. For us, though, I want to be a little more sophisticated. So actually, I haven't really made a mistake. I'll correct my self-correction. Instead, what I'm going to say is once the center point reaches once it goes far enough that the asteroid is completely off screen, once the asteroid size passes the edge of the screen, then we actually move. So the x and y velocity can be like a random number. Let's see. But we want the asteroids to be moving in the same speed, whatever direction they're moving, and give them a random movement direction. So to do that, we should have a common speed that they all start at, but a random direction they rotate at. So we're going to say, we're going to have a var, because we don't need to keep it, and we're not going to make it a member variable. We're going to say velocity, oops, or we're going to say direction. And that can be math random tau. Tau times math random. This will be different from the asteroid's display angle, which is what this is, what the theta is. Instead, it's going to be this direction. So we're going to do math dot, and we're going to do direction. The x velocity should be cosine. The y velocity should be sine. And then we're going to have asteroid speed times this. So we haven't defined the speed, so let's do that now. I think the speed should be pixels per second. So let's make that 32. We'll just have to eyeball it. I could do some math and figure out what a good speed should be, but I'm just going to eyeball it and see what looks good. So I'm going to say 32. I'm going to put a comment here because it's not totally clear. Pixels per second, and I'll explain how that works in a minute. But we've given a random movement direction, velocity, for this asteroid, and we've assigned velocity values in the x and y directions, and the asteroid's going to keep this forever. It's not going to accelerate. It's just going to move in this direction forever until it gets destroyed. That will probably leave for another time because this is already going on about as long as I was going to, and I haven't even gotten to the game loop yet. But this frame step is effectively our game loop. And we're going to have to, before we render the asteroid, we're going to have to make it move. The render step is just showing what the asteroid looks like. But we're going to have, I'm going to call this process, actually. We're going to have a function called process with a single parameter called delta, which I will explain in a minute. And I think we want to have semicolons for these prototypes. Suffice it to say, prototype is saying that this member that we're adding, this function, is unique to each object, rather than being inherited from the class itself. So we've got this function called process, and every frame we're going to apply the asteroid's velocity to its position. So that's pretty simple. This dot x plus equals this dot x vel. The same with y. This dot y plus equals y vel, right? But there's a problem. Not everybody has the same frame rate. Frame rate actually fluctuates a lot, so every frame the asteroid is going to be jittering and moving at different speeds. We can't predict how fast the frame rate is going to be, and we can't do a lot to enforce a frame rate, at least not in JavaScript. There isn't really a good way. Instead, we're going to use this delta method, this delta variable, to calculate how much time has passed since the last frame. And how do we do that? Well, that's where the frame step function comes in, because request animation frame passes an argument to whatever function we give it, and that's a timestamp. So we're going to have previous timestamp is going to be, you know, a number. And we're going to do a little bit of stuff here. Prev times. There we go. So first time we run this, previous timestamp is going to be wrong. It's going to be 0, and then this number I think is meant to be the amount of milliseconds since the application started, in this case since the script started, something like that. It's kind of arbitrary. I think there's not a really good definition on exactly what the value of the timestamp is. Our use of it is going to be relative. The only point that we need to know is that the timestamp is relative to previous timestamps. So if it's 0, that means we're running this frame step function for the first time because I said it was 0. And so we assign the timestamp. We're not going to actually do any updating. But I'm going to say delta. We're going to calculate the delta. I believe the timestamp is in milliseconds, but we want to convert it to minutes. So what I'm going to say is timestamp. Oh, we're going to have to do this. We're going to have to use parentheses. Timestamp minus previous timestamp divided by 1,000. Oops, there we go. This will give us a delta in seconds. That'll make it easier to calculate stuff as we go on. It'll be easier to think about the time since the last frame in seconds than milliseconds. Okay, so test asteroid. We're going to call the process method on our test asteroid with the delta that we just calculated, and then we're going to render. So what the heck is going on here? There's a whole lot that's going on. That's right. Before we call the next frame step, we need to store the current timestamp in our previous timestamp variable. We want to do this after we've done everything else in this function, so that the next time our frame step gets called, the next time a frame gets rendered, we can calculate the time between the new timestamp and the last time the frame was rendered. That's what this is for. So this will give us the number of milliseconds since the last frame was rendered. If you're looking at 60 hertz monitor refresh rate, that's going to be something like 16 milliseconds. It's actually more like 16.66 repeating forever, but milliseconds don't get divided that small, so more or less it'll be about 16. We divide by 1,000 and we get our delta. But this fluctuates, and so rather than assuming how much time has passed since the last frame, we calculate based on what the system tells us. And luckily we get this information to work with, so we can do stuff like this variable processing. This isn't the best way to do this, but it's the simplest way for this tutorial. I might come back another time and do a better way, because there are problems with this exact method, but for now we'll just do it this way. Now, up till now we've just been rendering one time, some static objects on the screen that don't move. Now we've got this frame step. Every frame we're going to be draw, 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 draw. Every frame we're also moving the asteroid along its random velocity. And there's one step that I've missed, but I'll be able to demonstrate it by refreshing the page if it doesn't show up the first time. So assuming I did it correctly and there aren't any mistakes, there's our asteroid just floating along. Hopefully the stream is smooth so that it actually looks nice. Now, of course, it's going to keep moving off screen and keep going. And that's no good for us. We want it to loop around like I was talking about before. So we need to go back to our script and we need to add some more stuff to this process method. So rather than actually assigning to the member right away, I'm going to say next. Oops, there we go. We're going to store the next position in some variables first. Then we're going to do some checks. If next x less than negative asteroid size. Oops. Let's do this. Asteroid size. There we go. I think putting the minus sign ahead of it meant that the autocomplete didn't want to work. So if the x position is less than the asteroid radius negative, which means that it's gone past, the asteroid has gone completely past the left edge of the screen, next x plus equals render context canvas width. We add the width of the entire canvas to our asteroid, and it'll be popped all the way over to the right side of the screen. Problem is, it'll appear on the right side of the screen with the right edge that just passed the canvas aligning with the edge of the right canvas. So it'll like pop into existence on the right edge, which is not what we want. We want it to we want to move it beyond the right edge of the screen and then come back onto it. So what we do here is instead we add a little bit more. We're going to add 2 times the asteroid size. Which actually I'm going to simplify and I'm going to say asteroid diameter. Here we go. Diameter. Just to save space. Because again, multiplication can be an expensive arithmetic operation. It also looks a little cleaner. Else, if next x is greater than render context canvas width. So if we have the opposite, there are going to be three cases. Either the X position is within the rendering space that we want it to be, it's too far left, or it's too far right. So if it's greater than the width plus asteroid size, which means that including the radius, the entire asteroid is out of view, we subtract render convex canvas width plus asteroid diameter. There. And having done that, we can say this x equals next x. I don't know why I was just typing and erasing there, but we can assign the next x position now to the asteroid's x position. And I'll save some time by copying all of this and then just changing, oops, not all of them, and changing all the x's to y's and all the widths to heights. And that should work. Let's go back to the browser, reload. The speed's too slow. I'm gonna, without switching back too fast, I'm gonna make, how much faster should I go? I'll go like 8 times faster. That's better. We should see the change a little faster. So now, so the asteroid is a bit bigger than 16 times 3. You can see that it snaps, that it kind of pops away. I'm thinking the size might actually be, at a scale of 1, I think the size might actually be more like 24 than 16. That's a good reason, by the way. That's a good reason to have constants like this, because I can just change, I can change the number to, say 20. And all instances of the size and the diameter, because of the way I set this up, both of them will get updated everywhere else. They're referenced in such a way that it's easy for us to make these changes. 20 seems like it's still, oh, I know the mistake I made. These diameters need to be multiplied by the scale of the asteroid. Oops, deck G by accident. So does the asteroid size. There we are. So, programming can get complicated pretty fast. There's a lot of text that we have to deal with. This should be a little smoother now. Even I changed the size back to 16. And yeah, you can see it's a lot smoother. It looks more like it's screen wrapping with a little margin. You can imagine that around the edges, there's a little bit of space where the asteroids kind of exist, just slightly out of view. So we've done all of that. Oh, I'm in the wrong window. There we are. We've done all of that, and we've got some automatic stuff going. We don't yet have player control, though. And we don't have a method, we don't have any methods to move the player ship. And at this point, it might actually be good to, like with our asteroid, to make a player object, a player class that we can instantiate and call methods on, like process and render. So I think I'm going to have to save that for a future stream, because even setting aside almost 2 hours, I hardly got anything. I only got this far, pretty brief. But it just goes to show how even something this simple, as simple of a game as this, can take a lot of work to do. Granted, I'm working without an engine. I'm basically building an engine myself. but this is the kind of thing I like to do. I don't know, maybe I'm a masochist. Um, but thank you for joining me. I'll come back again some other time out of the blue to do one of these, do a little bit more of asteroids in the future. So keep an eye out for that. Um, Probably won't do that before the Monday stream. So I guess the next time you see me, it'll be on Monday doing more Monster Hunter. See you then.